It's also a pleasure to be here. It turns out that I spent most of the summers of my childhood only a few kilometers away from here, and I'd never been to this school, so it's really nice to be here. So today I will talk about exoplanet detection, exoplanet characterization. How will we manage to find how frequently there is life in the universe by looking at exoplanets? And we'll look notably at applications to the TRAPPIST-1 planetary system, currently our most optimal place to search for evidence of biology beyond the solar system. So as a quick recap, TRAPPIST-1 is a star right there, just south of the celestial equator and north of the ecliptic. And it's among the 500 closest stars to the Sun. And around it we found this system, which is absolutely remarkable in every sense of the word. You have 7 worlds with a distance here of only 6% of the distance between Earth and the Sun. This is a really packed system. Now the star at the center is tiny. It's only 9% of the mass of the Sun. It's very cold, and because it's cold, despite the planets being really close to the star, we consider all of them to be temperate, meaning that possibly under a certain, sometimes very exotic geologic and atmospheric condition, you could expect that at least on a part of the surface, water could remain liquid for billions of years. And so this becomes basically a sort of license for us to explore more, try to go and see those planets and assess for the first time empirically whether habitability is achieved on any of those, and indeed whether any of the planets turn out to be inhabited. What's incredible, to just give you a sense of the scale, is that you see these two planets are going to come in conjunction here. If you're sitting on this one and looking up here, the distance there is only 3 times the Earth-Moon distance. And so you would see this planet here as like about twice the size of the disk of the Moon in the sky. This is incredible. If you were on that planet, essentially, looking up with a small telescope, you'd be able to see cities up in the sky. I think TRAPPIST-1 kind of fascinates us, has fascinated even us who have discovered it, because of how beautiful I think the system is and how surprising it has been. So our motivation there, and I guess the motivation of most of us in the room, is to answer more or less this question: is there life elsewhere? Now I think if I were to quiz you, if I were to quiz most astronomers, I think almost invariably you would get this answer. The reason we think that is because of the Copernican principle. We live only on but one planet, around but one star, of which there exist 100 billion in our galaxy, of which there are also 100 billion. So surely somewhere else life must have started. There's nothing special about Earth. That's something we still need to assess. But because of this sort of thought, astronomers came up with a few concepts. One of them is called Earth 2.0, or the Earth twin, a copy of the Earth around a copy of the Sun. And the idea behind finding such an Earth, or an Earth twin, is that things started here, so if we replicate similar conditions elsewhere, maybe we have a good shot at finding life elsewhere. And although the concept is sound, there are a few problems with it. One is time, the time it takes to find one. Another is that I think invariably also it would be really strange if Earth had the only template for habitability in the cosmos. And I think we need to think a little wider. And the first slides that I will spend on is to convince you of how diverse the exoplanet population is, how we need to account for environments that are widely different from those of Earth, and that in the end the Sun-Earth system represents only a minority of planets and systems in our galaxy. And if there is anything that surprises me in biology, it's how diverse biology is, how much more diverse it is than exoplanets. And so I think we need to keep an open mind there, and maybe there are worlds that are more habitable than ours, although the conditions here certainly look quite clement. So how do you study a far-removed world? That's essentially what we will ask today. I will first go through a few detection methods. We'll try to find which one are most suited to answer our question, which ones have matured, which one remain still to make essential detections. And then from those we'll move on to characterization of the atmosphere. An atmosphere is important. It's not that I think an atmosphere is required for life to exist. I think subsurface life can exist on an atmosphere-less world. It's just that you need an atmosphere. You absolutely need an atmosphere to detect life beyond the confine of the solar system, because the atmosphere is a reservoir. It's a receptacle of biologically produced gases. If you have nowhere to store the gas, then you can't detect the presence of biology. So we need an atmosphere. So we'll see how we study those, and then we'll apply that knowledge to the TRAPPIST-1 system and try to see the logic that pushed us to go through the detection and the search for planets around such a strange star. For a long time, so this concept here, the plurality of world, is a concept that dates back from the 3rd century before the Common Era. Epicurus was writing back then on the infinity of worlds, how similar and different they are, and was part of a philosophical tradition where everything was possible. There was an infinite number of solutions, and every possibility must exist somewhere in the universe. And this is something that, as a physicist, we know that cannot exist. It cannot exist because we have physical laws. So effectively, not everything is possible. Physical laws are shaping the universe. And yet, in exoplanets, strangely, that old philosophical concept has endured. And we now call it the diversity of exoplanets. These are all the things that we can measure about planets. You see the list is actually getting quite long. It's going to get actually a little better. And you would be hard-pressed to find any correlation between any of these parameters. Oddly, things spread out. The best thing that you have is between mass and radius. I mean, we will see that. But yet, for mass and radius, you can cover 4 orders of magnitude in mass, and yet change your radius only by a factor 2. So there is really little variation. A lot of variation, very little correlation out there. And that's what really surprises me. So let's look at this diversity and then use the fact that things are so diverse to actually help our search. So first, the exoplanet detection methods. There are a few methods, and we won't look at all of them, but these are the main ones: radial velocities, transit, microlensing, direct imaging, and astrometry. Now, we have to bear in mind that we want both to detect a planet and study its atmosphere. So microlensing, although it's a very nice method for detecting planets as low in mass as an Earth mass, unfortunately does not provide us with a means to study the planet in detail. So we're going to take that one out from today because it's not as relevant. Astrometry is a method that has yet to deliver, but will probably deliver very soon thanks to Gaia. Now, astrometry at the moment is only limited to systems that are fairly far from the star, so less likely to be habitable, and mostly large planets, so planets of Jupiter mass and above. So we're going to remove, I think, those two right here, leaving them in our mind for the future, but not for the immediate consideration. The first one we're going to look at are radial velocities here. So the way we're going to do it is by basically parsing the stellar light through a prism. If you go at high resolution, you get this sort of picture. So this is the sun. You see here all sorts of absorption lines created by atomic species within the atmosphere of the sun. And this pattern is a pattern that essentially is always the same everywhere that you look. I think there is something actually remarkably poetic about physics, that these sort of things are universal in the purest, most literal sense. They exist everywhere and at any time through space. So this pattern we know of from laboratory experiments, and if we find that the pattern here shifted in wavelength, we know that the star must have moved. And so in a nutshell, that's what you see. If you have a planet and a star, the planet will displace the source of light, and as you see that, it will basically shift this pattern from blue to red shift. So as the star basically moves away from you, you have a red shift. As it comes away towards you, you have a blue shift. And this you can do fairly well. This method now is well tried. These are data taken on the 55 Cancri system. You see here a long oscillation from an outer planet. You can see that here the data is not quite the same as there, and that's also because the star has a magnetic cycle along it that messes up a bit with the measurements. And you see this sort of ratty part here. This system has 5 planets, one that is pretty massive. This is the second closest to the star, which is pretty massive and oscillating really fast, and another which is quite far, and a number of planets that have lower masses. So this we know fairly well. The relations that we have are the following. So for a Jupiter-like planet, the amplitude, so the semi-amplitude, so that's basically half of the total amplitude that you have here, will be 12.5 meters per second for an orbital period of Jupiter. So if you have 11.9 above that, you get 1. Then Jupiter mass, you get 1. Solar mass, you get 1. So you get 12.5. If you have something a tenth of the mass of Jupiter, then you get a tenth of the amplitude right there for a period of 12 years. For Earth, this number is 9 centimeters per second for an Earth-like planet around a Sun-like star at a similar distance Earth occupies from the Sun. So this is small. This velocity here is the velocity that Usain Bolt achieves when he breaks his records. Just to give an answer, and this is probably the speed of a walking duck if you've seen some in the park of La Tèche. So using this method, what have we discovered through 20 years of discovery? So first, let's place the solar system into a diagram that we will use. So we have mass here. You see here units of Jupiter. Whoop. Jupiter here, 12 years. Saturn, Uranus, and Neptune. We have Venus and Earth. Mercury is right down below, and Mars is right down below here. And what we've discovered is this. So a very diverse population, as you can see. It fills essentially most of the diagram. We'll understand why there isn't so much here. This is filling a lot of the diagram, and we're really happy about this. That's how we've started discovering this diversity. You have 3 main populations. These are called the hot Jupiters. Hot Jupiters are actually quite rare. They're typically planets more or less of the mass of Jupiter, but with orbits below 10 days. And these exist around one star like the Sun in about 200. So rare. The fact that there is such an overdensity is because they're the easiest to detect. Then we have the warm and cold Jupiters that are around here. And if you take a line through here, and you find that about 10 to 15% of single Sun-like stars have a planet which we could classify as a gas giant somewhere in a system. In addition, the population that is most surprising is probably this one. This population here we call super-Earth. You see they're above Earth in mass, but sub-Neptune. They're just below the mass of Neptune. They really are filling a gap in mass between these two type of planets that we have. They're also mostly within the orbit of Mercury. Mercury would be here, right? So most of these guys are more massive than the Earth within the orbit of Mercury. And around half of Sun-like stars have a super-Earth. And that's really surprising. And if you count this 50% and you count this 15%, you basically have an image that starts building up that 2/3 of planetary system are different from the solar system. And in fact, the mere fact that half of them have something that we don't have is telling us that the solar system probably did not partake in a main mechanism of planet formation in the galaxy. And that has implications in our search for life elsewhere. It seems that we're not in a norm. It does not mean that we're particularly special, but it does mean that what we have under our very eyes and can study so very well with probes is not necessarily representative of what's out there. So let's place a few limits here. So you see here this 10 meters per second. So the first experiments were basically blocked here. So and you can see actually that Jupiter is just about detectable with this sort of precision. The fact that you have few planets here is because that takes 20 years, and we've been discovering planets for 20 years. To detect a planet, you need 2 oscillations, so it takes a while to find these things. So progressively, we're filling in the diagram right here. Now, the best experiments at 1 meter a second, so this population was detected, but now they've started a bit late compared to the one at 10 meters per second, so they're catching up progressively in this area. The lack of objects here is a source of debate, whether it's a real lack or whether it's because we have some problem with our data analysis. The lack of objects here is real, and this one as well. And now the best instruments are about 20 to 30 meters per second, centimeters, yeah, just about here. So you can see these objects just being discovered. Earth essentially still remains away from our current capability. So finding a true Earth analog using the radial velocity method is so far hard and not yet in our current capability. Now, what else have we detected with the radial velocity method? We've detected another element of diversity, and I think that diversity is important. This is eccentricity here that you have from 0 to 1, 0 being a circular orbit, 1 being a parabolic orbit, so an open, unbound trajectory. And you can find that planets, essentially compared to the solar system, which is here right about 0 except for Mercury, basically fills a huge part of the parameter space. And that's also something that you have to bear in mind. If you want your Earth here to have a stable climate, like you would think you would need to sustain a biosphere, then we have to account the fact that many planets do not have eccentric circular orbits, and those might go away from our consideration. However, I must point out that here you saturate a bit. You have lots of systems here that are just about 0, and it's hard to distinguish them. So many systems are close to 0, especially if they are in multiplanetary systems. And the TRAPPIST-1 planets, particularly, are very close to 0. The final part that I will show you from this is the mass-radius diagram. So we haven't looked at how we measure radius. We'll do that from the transit method. But essentially, if you have mass and radius, you can plot them together, and you see there's a sort of relation. That's probably the best one that we have. So far, you see here Earth and Venus, Uranus and Neptune, Saturn and Jupiter. And you see that there's a continuum of planets, essentially. There is no clear break between the gas giants, the ice giants, and the rocky worlds. And right here, there might actually be something slightly, a slight gap that is not so visible in this diagram between the super-Earth, which we would call the rocky planets more massive than Earth, and the sub-Neptune, which would be those that have a substantial gas envelope, slightly more massive. But essentially that's what it is. In terms of mass, if you are 0.1 of a Jupiter mass, you're about here, and you can go right up to 100 Jupiter mass, and you will basically get the same radius. So that's also one of the reasons I think that radius is not there's not much of a correlation between mass and radius. All right, so now we've looked at radial velocity, we've gone around. Radial velocities are interesting, but are a little short in our search for a world that we can study. Besides that, radial velocities also don't give you much yet in terms of atmospheric properties, although we'll see that there is some prospect in the future. So now let's move to direct imaging. Direct imaging is trying to resolve your star and your planet from one another. In radial velocity, you don't resolve the planet, you just see the star, what will the effect the planet has on the star. So here we have a normalized black body. It's normalized to 1 for the Sun. I'm sorry for the contrast here. If you have a planet like a hot Jupiter, and I hope some of the lines will show up. Yeah, so you have here this line. Essentially this line here, there's another one, unfortunately, that you don't quite see right there. That would be for an albedo of 1. So if your planet reflects perfectly, it would have a black body exactly under the Sun right there with a perfect reflectivity. Now most hot Jupiters, most gas giants, it turns out, close to the star have a low albedo, 5%. So they absorb 95% of the stellar radiation. And if they absorb it, then they must emit it as well. And so if they emit it, you can plot essentially another black body right there. That is the emission spectrum. And then you combine both of them, and then that gives you a sort of sense of how much of a difference to the star you have. Now, if you have direct imaging, that's basically the sort of signal that you want to find. 70 parts per million in the visible, you have 3 orders of magnitude more in the infrared. So most searches for direct imaging are concentrating in this area in the infrared, although this is still a hard signal to detect. Those relations are essentially ruled by these relations. You have here the change in flux, this drop in flux is the albedo, and then the radius of the planet over its separation to the star squared. So this is convenient because this is also something that we'll come back and get from transit. For an emission spectrum, like you have here, you have the radius of the planet over the radius of the star squared. Again, that's something that we get from transits. And if you're in the Rayleigh genes, and so this part of the black body, then you can just have a ratio of temperature. Now, how does that apply to Earth? And I think Earth will actually not be visible. So normally you would have seen here essentially a bump here. Earth is at 7.5 10 to the minus 10 in ratios, in flux ratio. And that's the problem that we have for detecting Earth using direct imaging. You have essentially a huge flux difference here that you need to achieve. And that's not just that, you also need to resolve it in terms of spatial dimension. So this is probably one of the most emblematic detected system using the direct imaging method. You have the star here. The sort of strange pattern that you see here is the suppression methods for the PSF, the point spread function of the star, and you have these dots. So this looks like a planet, this looks like a planet. Is this a planet, or is this a planet, or is this a planet? Well, you'll see. But essentially, what's important to know is that this central area that the star is blocking is about 20 AU here in diameter, so 10 AU. That's the orbit, essentially, of Saturn. Right? So you can't really get much closer than that. However, if you wait and you have the right thing, you can see here your planets moving. All 4 dots here are planets. This is the HR 8799 system. All are essentially beyond the orbit of Saturn. All have masses well above that of Jupiter from the models. But essentially, that's direct imaging, and now people are working to essentially improve the contrast ratio, so how much of a difference compared to the star influx you can reach, and also in order to reduce this essentially black area and get it tighter around the star. And we'll look again at another method eventually that helps do that. So direct imaging currently in terms of finding an Earth analog still has some severe shortcomings. So I think I'm not going to go much into that, and then we'll basically focus now on transits. Let's go back for a short instant to this diagram, so this mass period diagram. So we often use, astronomers often use this type of diagram to sort of pat ourselves on the back and say, well, see how much work we've done in 20 years. Isn't that great? It's beautiful. And yeah, sure. But what we often forget is that 95% of the dots that you see here are around single sun-like star. Just single sun-like stars. They have avoided essentially any other type of objects. And it turns out that half of the stars that you see at night are binary stars, and those are totally removed from our consideration. And it turns out that half of the stars in the sky you don't see, actually. So here is one, I think, of the most important diagrams of this presentation. This is a histogram of the stellar content of the solar neighborhood within 10 parsec volume, so a unit that we use in astronomy for distance, the nearest star being 1 parsec away, more or less. Here is basically the sun. A sun-like star would be in this bin here, and if you integrate that, you find about 15% of the stellar content of our galaxy is made of sun-like stars. But half of those are binary stars and taken away from the Earth twin sort of searches. So 7 to 8%, essentially the search for an Earth 2.0 revolves around 7 to 8% of the stellar content of our galaxy. What's fascinating is that half the stars in the sky are here, essentially. Very low, less than a quarter of the mass of the sun. And if there is one number, I think you need to remember from this presentation, is this 50%. This is actually also how I decide what to investigate. 50% is a big number and is worthy of consideration. 50% of stars are binary systems, and currently I have a big project trying to find planets in binary systems where you have 2 stars orbiting and then a planet around both of them. We call them circumbinary planets because it's useful to learn about planet formation. 50% of stars have masses less than a quarter of the mass of the sun, and that's the consideration that will basically keep us talking today, because TRAPPIST-1 is part of these. And 50% of single sun-like stars have a super-Earth, and I think that's a huge topic as well of consideration. But this number essentially tells you how similar and different those worlds are. They may look very alien and exotic, and yet they're also normal when you look at the whole of our galaxy. So let's look now at the transit method. That's basically what we'll keep on discussing for the remainder. With it, be it the transit or the radial velocity method, it's important. to know that the stellar flux, the way that we measure things essentially is that the stellar flux get affected by the presence of a planet. So we don't separate the signal of the planet to that of the star. They're combined, and then we somehow manage to remove the star. So that's important to bear in mind. And the same goes for atmosphere. So our knowledge of the star will always affect our measurements and our conclusions, and that's worth retaining. So how will we start exploring atmospheres? So for that, we will first look at the Moon and try to assess how we could study the atmosphere of the Earth as seen from a remote place and see what we would deduce from that exercise. And one of the easiest places to start is during a lunar eclipse. Now, during a lunar eclipse, what we have is the following configuration. We have the Sun, we have the Earth, and we have the Moon. And again, the contrast doesn't show the light right here. The only light that reaches the Moon is essentially sunlight that went through the atmosphere of the Earth, got essentially reprocessed by the atmosphere of the Earth. And if you place a spectrograph on the Moon, essentially that's what you measure. You measure here flux, and you measure wavelength here. You see there is less flux here than here, so the Moon looks red, right? It's red. And you don't need a spectrograph to know that, but essentially you find it on your spectrum as well. Here the white and the yellow are two different pieces of work, two different epochs and different locations on Earth. But essentially what you find is that you have this big structure here from oxygen, you have a big structure here from ozone, you actually find also a structure here of a nitrous oxide. So in addition to discovering a biomarker, you also can detect human stupidity right there. This is pollution. This was taken from an observatory near Beijing. So essentially, that's what we want to be able to reproduce elsewhere. Now, if you imagine yourself on the Moon while you have a lunar eclipse, what do you think will be visible? What is it that you will see? All right, picture it a bit. Now, fortunately, we have footage of that. That's the only one that we have. This was taken by Apollo 12 as they returned from the Moon to the Earth. It was taken with a handheld camera. And you see here, essentially, the atmosphere of our Earth. And the red hue that you have here, essentially, is not sunlight directly. It's sunlight reprocessed by our atmosphere, the same one that hit the Moon. Essentially, a lunar eclipse is 1,000 sunrises and sunsets all together. And if they had had a spectrograph, the astronauts would probably have deduced that from this narrow band here, they would have detected oxygen and the rest. And this is essentially what we want to identify in an exoplanet. We want to access this ring right there. So now, how do we do that? Let's try to see what a transiting planet looks like. So this is again footage by the Solar Dynamical Observatory of Venus transiting. Now, can anyone see the atmosphere of Venus here? And anyone see a ring right there? It's going to come by again, so that's the only occasion to see Venus transit in less than 100 years waiting. Up, there you go. Try to see the atmosphere, right? Impossible. We actually, compared to the inhomogeneities on the Sun, the planet itself is actually quite small. So how do we do that? What trick do we use? So that trick is called transmission spectroscopy. So if we have, and that's probably the method, the first method that will identify a biomarker on a planet outside the solar system. So when you have a transit, you have your star, you have your planet, you're the observer right there. You know the size of your planet from the deficit of flux that comes from the star. Now imagine that your planet has an atmosphere which, like Earth, scatters blue photons. It means that it's opaque to it right behind. So we use here a blue wavelength and we measure a size here. Now the red wavelength, just like they do during a lunar eclipse, will pass through unimpeded, right? You're here at sunrise or sunset, you see the sun being red, the Moon sees the sun as being red as well. And you will measure a slightly smaller size. And so by carefully measuring size as a function of wavelength, you can identify opacity sources within an atmosphere and match those opacities to the presence of molecule elsewhere. So this is all size. We always measure size in here. And in practical terms, that's what it looks like. So here you have the relative size of the planet to the star. Essentially, this is a measure just of the size. And then you see a slight change of size as with wavelength. And this is an absorption band. So the planet essentially becomes more opaque. Here it's a water band. So you have water in the atmosphere. The water essentially absorbs the stellar radiation. The planets look opaque. It looks therefore bigger than at this continuum wavelength. And so essentially you want to do that. And this method now has been applied to almost 80 gas giants so far. So we're well practiced to do it. Now there's another way also to look at atmosphere, also using a sort of transiting method. Here the planet goes in front of the star. And what you probe is here, just this terminator, this day to night region, which is also a special region for any planet. But what you can do is wait for the planet to go behind the star. Then you get this data. Here you have the star flux plus planet flux. Then the planet goes behind the star, you only see the stellar flux, and then up the planet reappears, and you get again your star plus planet. And so this here, deficit here, that's your planet. So if you measure that, you can get a spectrum. And essentially what rules this is the same equation that we had before. This essentially that we saw for direct imaging. So now you measure essentially a flux ratio here, you measure a flux ratio here, you see this is at a different wavelength, it looks deeper, and you plot them as a function of wavelength. And for the same planet that we had a transmission spectrum, you see here an emission spectrum, and here you see an absorption band because water in this case is absorbing the emerging flux from the planet, so it goes down, and you see here a clear detection of that water band right there. And I'm sorry that you can't see the scale, but here we essentially have the same sort of scale that we had during direct imaging for a hot Jupiter, this sort of 100 parts per million, more or less. Now this emission or reflection spectroscopy, so this is emission in that it's in the infrared part of the spectrum. You can also do it for the reflected part of the spectrum in the visible, but that's a little harder and few measurements exist for that. Now this is similar to another experiment we can make on the moon, which is the Earth shine. So the Earth shine is when the moon is dark but not quite dark. You see here the thinnest of crescent on the moon. And yet the moon is not completely black. It has a sort of grayish, bluish hue. And the reason for that is because we are in such a configuration. The sun emits light in every direction, some hits the Earth, most of it gets essentially reflected, some of it hits the backside of the moon, the dark side of the moon. It gets emitted in every direction, but you're here. It's night side, it's nighttime, and you see the moon, and essentially the sort of bluish light, this Earth shine that you see, is a sort of integrated image of the day side of the Earth shining on the dark side of the moon. So in many ways, again, I think it's quite poetic that sometimes by night, if you look up at the moon, you can see the day side of the Earth in a way. Now, if you place a spectrograph on the moon during that time, you get this spectrum, which is essentially the reflection spectrum of the Earth, and you have essentially flux here and wavelength the same way. You see that it's bright in the blue and darker in the red. That's because we have blue sky, essentially. And you see this structure. And that's, I think, what's important. This measurement is harder to make, but it has a lot more information. You have CO2, you have water, you have methane, you have, again, the ozone layer here, you have the scattering slope, the Rayleigh scattering here, which tells you about the particles in the atmosphere, so the color of the sky. We want to measure the color of the sky of exoplanets, not find life, just the sky color is nice. And here you see that this goes up, and that's what we call the vegetation red edge. So that's the fact that photosynthesis needs to use a pigment, and that pigment reflects in infrared. Plants, I believe, use it to cool down, notably. So essentially this has been posited as a way to detect not just the presence of biomarkers, but actually the presence of biology itself. So these are methods for atmospheres. Now there are a few other methods that we'll go through that are more experimental in that they've been used on much fewer systems, but might be useful in the future. One of them is to make maps of exoplanets. And essentially, here is how it works. You wait for your planet to go behind the star, and as you can see, as it goes behind the star, progressively it gets cut here by the stellar surface. And as it re-emerges, you get cuts in another way. And so if you have lines in this way and lines in this way, you have latitude and you have longitude. And so you basically can create two maps like this, and if you combine them, you end up with something that can show you more or less a topographic surface feature. So that's something that hopefully we'll be able to do in the future, and I'll show you some of the reasons why this might be very handy in some cases. So using all of those methods, what do we learn? Because that's what's important. What do we learn about them? So we learn, and I think that's really important part. First, we learn about the existence of an atmosphere. As I said, establishing that you have an atmosphere on a planet is the first step that you should have in order to eventually detect biology. You measure chemical abundances, you can get the fraction of cloud cover from transmission spectroscopy, and that's because on the edge of the planet, if you have a bit of cloud or higher opacity, it will basically block in a sort of gray way, so uniformly through wavelength. It will block your signal, and so you can sort of get an idea of this. You can get from emission spectroscopy, particularly the vertical temperature pressure profile, so how temperature changes with altitude within the atmosphere. How wiggly it is will depend on how many layers you have in your atmosphere, how many cloud layers are likely to exist. If for some reason you observe a planet that has few of these wiggles or is particularly clear, you might use these profiles to get down to surface conditions, and using reflection and emission spectroscopy, sometimes you get down to the surface as well. Using variations in the transmission or emission spectrum, you can also do some weather monitoring. And there's one planet, 55 Cancri E, for which some changes here in transmission and emission are being posited as being caused by volcanism, notably as a sort of extreme sort of weather monitoring. Those volcanoes essentially emitting large amount of opaque gases and particles. Of course, biomarkers, this is linked to that. I think biomarkers don't exist in isolation. You have to see how well balanced they are with the rest of the atmosphere, or actually out of balance they are chemically. You might be able to assess the presence of liquid water as well, and that's because if you have liquid water, some of it will likely evaporate, some of which will likely be photolyzed by the sun. And if you look in the UV around the Earth, we have actually a large corona around the Earth, which is caused by hydrogen escaping due to this process. And there is also the prospect of measuring isotopes, and that's what I'll go down into, because I think that's something quite fascinating as a prospect. So far, most of our spectroscopy of an atmosphere was at low resolution. However, if you go at high resolution, you see something quite interesting. So you have here again the flux of your planet and the flux of your star. And you see it's a very small number, but here is basically going to be the continuum of your planet. And then if your planet has carbon monoxide, it will absorb, and you see this very narrow spectrum, narrow bands, sorry. And the difference between each of those bands here is due to the vibrations between the carbon and the oxygen atom. So that's the vibrational band of the molecule. Now, if you have carbon-12 or carbon-13, this will change the masses of that dipole, and you essentially will change this frequency comb right there. So you will have a slightly different pattern, and that will allow you to detect whether you have carbon-12 or carbon-13. Now that can be replicated as well for other molecules, but essentially it boils down to that. And it's not that you will detect each of those lines using this method, but rather because you have hundreds of lines, as you can see here, you can build your signal up using each of those. What I like about this high-resolution view of atmospheres is that it combines radial velocity, it combines transit, it combines everything together, and we'll see it combines also very well with direct imaging. So here is actually a view of a transiting planet using this method. You have essentially wavelength here and time there. You see the planet transiting here. You see here tellurics within the Earth's atmosphere. And here you see those bands essentially, which is the spectrum of the planet moving by hundreds of kilometers per second as it orbits its star. So instead of resolving the planet here, spatially you resolve it spectroscopically and you directly detect the light from the planet. So it's actually, it's been done now on about a handful, maybe a little more, of planets, but it's something that will likely increase as we get to larger and larger mirror, notably with the extremely large telescope in Chile. And the final method that I will point out is actually a combination of this method, high-resolution spectroscopy, with direct imaging, essentially. That might be actually already doable for Proxima b, so one of the closest habitable zone planet to the solar system, Ross 128 and Gliss 411b. And this was done in the paper that Ignace Nellen did in 2015. What you have here is essentially, again, this contrast ratio, the same thing that we had when we were looking at black bodies, except that you here see the PSF, so that's the stellar profile. It's at 1 here, normalized to 1. And essentially, if you want to find a planet, it needs to sort of peak out here. So here I have a ratio here of 10 to the 3. That imaging can give you. So here you have your distance, essentially, from the center of the star. Here is the flux ratio. And essentially, if your planet is there, you can reach this gap by using spectroscopy. And you see here, potentially this method has already reached 10 to the minus 7, which is still 2 or 3 orders of magnitude away from an Earth, but is getting mightily close. So that's, I think, one of the most interesting prospects. A reason why this works is that rather than in direct imaging trying to separate the star from the planet that is here and try to assess whether this is noise or whether it's a planet, you see there's another spot here and another spot here that have more or less the same contrast. Here, if you turn it and you have your x, y, and then in a third dimension you have your velocity, your planet will have its own velocity and it will basically move around the star in a well-behaved and a predictable way. So that's why this method works, and I think is probably one of the main ways we will do atmospheric work in the future. We're about halfway now. Let's try to go and search for another Earth. Let's go and try to find TRAPPIST-1 using essentially what we've learned so far. So how will we do that practically? So let's look at the transit method a tad more. We have a star like the Sun, and then let's transit a planet the size of Jupiter around it. What do we see? So as an astronomer, you don't see this. You don't resolve the planet, you don't even resolve the star. You only have a point source. What you have is essentially that the flux goes from 100 to 99% for a few hours, essentially. That's the depth of transit that you have. Now, if you want to study the atmosphere of that planet, essentially what you're searching is a change in the depth here. And the atmosphere here is barely visible, and so will the change in depth. The change in depth is just there, and unfortunately the contrast doesn't quite see it. This is 0.01%. So 1/100th of that signal is a change of depth that you want, that you can achieve essentially to do this transmission spectroscopy. And that's something you can do. You can use the Hubble Space Telescope to do that. You can use the VLT in Chile to do this. So we've done that repeatedly. Now, the reason we can do that is because we know when the planet will transit and where it will transit in the sky, around which star. The problem comes with finding a random planet using this sort of precision. And that's what faces us with a true Earth analog. So Earth transiting the Sun, look at this. Look at that. Too small. Right? Not just about as big as this. Here, the transit here has been amplified by a factor 10, so you could see it. Essentially, finding an Earth analog is equivalent to studying an atmosphere on a gas giant. It is the same signal, except that you don't know where the planet will transit and you don't know when. Earth transits once a year for 10 hours. So it's very hard to find out, to find that. Now, people have tried this because you need to do that. And that answer was the Kepler spacecraft. So actually, just before going that, essentially the depth here that you have, this depth is RP over R star. Again, two quantities that you will recognize. If your planet is 1/10 of the star size, essentially this is 100th, and that's what you find here. And the problem is that the Earth is basically 1/10 of 1/10, essentially. Finding a mission that can achieve photometric precision required, as if you were to detect an atmosphere but on hundreds of thousands of stars at once, was quite a challenge. And NASA answered that and decided to make Kepler. Kepler was a hugely successful mission. It found thousands of planets. However, its primary goal was to assess the occurrence rate of true Earth analog. And unfortunately, in that goal, it has miserably failed, and that's too bad. It's really sad, and it's not because people had done something wrong. It just turns out that stars are a little too buoyant and kind of missed the area where Earth is. There's actually one point here, however, it has only a 70% chance of being a true detection, a 1 sigma detection of a planet. And it's sad. I mean, that was actually really sad, because it's a mixture of feeling, right? Thousands of planets detected, but not where you want them to be. So what do you do? What can we do? Well, we can send another one, but then it doesn't change the fact that the stars are still buoyant, so you need to observe more. It's hard. Well, the thought that we had is that, okay, well, we need to figure something out from that. So if we go back to this equation here, now, if you change the size here, you change the depth there, right? But what if instead you keep this constant, and then you change the stellar radius? If you decrease that by a factor 10, then this should go back to 1%. And in fact, that's basically the story of TRAPPIST-1. Let's shrink the star. It's an easy thing to do. Well, it turns out it's easy because nature has provided us many. But essentially, when you go for a small star, the contrast of your planet to the star is a lot higher. You get back to 1%, and then you can do this work from the ground. You don't need a spacecraft anymore. The other thing that happens, and these are the equations for the transmission spectroscopy. So you have here your depth as a function of wavelength, which is your depth from here, plus this factor, which is here essentially the radius of the planet, the scale height of the atmosphere over the radius of the star. So you get, again, two sizes here, which correspond to this square here. And the scale height is the temperature of your atmosphere, which you know from the distance of the planet to the star, the mean molecular weight of your atmosphere, and the gravity, which you can also assess. So shrinking your star basically makes this bigger and makes this bigger by the same amount, by a factor 100. So you find your planet has a signal 100 times larger, and your atmosphere has a signal 100 times larger as well. So you get two advantages for the price of one, right? I'm going to sell you that. But it's not alone. You have other advantages too. Once you've set yourself on a small star, other things come for free. It turns out that a planet capable of hosting and retaining water in a liquid form will essentially be closer to the star. And that's hugely important. Earth around the Sun, it takes 1 year. Hard to find, hard to confirm, hard to study. Here, around TRAPPIST-1, it takes 1 week. Easy to find, easy to confirm, easy to study. It's a lot easier, in fact. And another thing comes again for free. If you're close to the star, the chance that you will have a transiting planet gets enhanced as well. And the reason is the following. If your planet is there close to the star, the fraction of stars that can see this planet in transit is essentially comprised within this cone here, compared to basically a line that would be here. So you see a huge fraction of the sky here can see this planet transiting. See from this star, they see the planet, boom, it interrupts the star. If you move far and further, you can see that this cone reduces dramatically. It reduces with actually an inverse law. So being close to the star actually means that more planets will come in transit just because of geometric concern, which means that you need to survey less stars, making it again easier. And then we had to work with what is given to us essentially. Soon, hopefully, I put a question mark, I hope we'll get that by 2021, the James Webb will be launched. So that's a joint project between the Canadian, the European, and the American space agencies. This is probably the most sophisticated spacecraft that we'll have launched. And it has the instruments that are capable of doing this transmission spectroscopy for an Earth analog. Now, it could do it on an Earth twin, except that one, we don't have that target, and two, you need 15 transits to achieve a 5 sigma detection of the atmosphere. And 15 transit means 15 years. 15 years of work. And it turns out that this main mission is 5 years, and it might be extended to 10. But 15 years is actually only the lowest amount that you can get, because sometimes the transits will happen while that star is behind the sun. And so really trying to analyze the atmosphere of an Earth twin using the James Webb is more like 20 to 30 years of work. It's extremely long. You get dominated by orbital timescale for this. And you still don't have a target. So if we put everything together in one diagram, what have we learned? So here we have star mass, and basically all those curves plot essentially a planet with the same equilibrium temperature as the Earth around each of those stars. So the Sun is here. The probability of transit is 0.4% for an Earth-like planet around a Sun-like star. And if you go to the low-mass star, you get to 4%. So you have an order of magnitude improvement. Transit depth goes from 0.01 to 1% here. So that's 2 orders of magnitude. And then the number of orbits per year goes from 1 transit per year to essentially 1 per week when you reach 0.1 solar mass right there. And the pink area is where there are enough transits within the main mission lifetime of James Webb. So if you have a habitable zone planet around a 0.2 solar mass star, you won't get enough transit during the entire James Webb mission to reach a 5 sigma on your atmosphere. So great, you have a habitable planet, but you can't study its climate, and you can't find out whether it has biomarkers. So we are limited to this area, and these are essentially the ultra-cool stars, the ultra-cool dwarfs. And that's why we decided to build Speculoos. The reason being that TESS, the current space mission run by NASA, is basically just not reaching the right area. MERS, our main competitors on the ground, are also just skimming the right area as well. And so we dreamed of essentially this project called Speculoos. Speculoos is the search for planets eclipsing ultra-cool stars. It's a stretch, but it's a very delicious Belgian biscuit, so it was too good to miss. And that's a project run, so the PI is Michael Gillon at the University of Liège, and we work in a consortium involving Cambridge, MIT, Bern, and Birmingham. And Speculoos, the project of Speculoos is essentially now become actually a reality. We have 4 telescopes. These are the 4 telescopes. They are robotic. In principle, you still need to press a couple buttons to start them, but they're mainly automatic. They're 1 meter in diameter, and they're observing from the best site in the world at Cerro Paranal in Chile. And here are telescopes. Look how pretty they are. Each have a different color, right? Oh, that's so nice. Unlike the ESO telescope, which are just boring blue. And the reason why we go to Chile, the reason we go to Paranal, is just because for those of you that are not astronomers, and I'm sorry you can't actually appreciate the beauty, it's just incredible. So if we had a good contrast, you will see that the sky here is not dark. It's actually gray compared to the Earth, which is dark. And you have a view on stars that is absolutely unparalleled out there. Meaning that actually your photometric precision, your ability to discover a signal is enhanced. The thing that you see here are planes. We hate those. The thing that you see shooting here is a laser, which sometimes is used to detect planets or search for planets using the direct imaging method. And what's interesting here is that you have here the galactic plane. This is absolutely stunning. The galactic center is just about to arrive, and when you spend with the galactic center in the moonless night, you actually see your shadow on the ground after 20 minutes, which is just mad. Where is it here? Yeah, the star that just set here was Alpha Centauri. Essentially, the conditions are great, and the reason the stars are disappearing is not daybreak, that's the moon. And so you can imagine astronomers have a sort of love-hate relationship with the moon because you can't see quite as well, and now it's daybreak. So Chile is just fascinating. That's why we want to go there. Now, building Speculoos is expensive, and so it took several years of convincing, and the convincing started essentially with TRAPPIST. And TRAPPIST, turns out, is another acronym. It's the Transiting Planets and Planetesimal Small Telescope. Right? Yeah, another Belgian product. I have it on good authority that the next one will be called Moulfrit. We still have to find out what it will mean. And so Michael Gillon had essentially this telescope. It's a 60 centimeters, slightly smaller. We used it to find many hot Jupiters, or actually sustain the confirmation of many transiting hot Jupiters. And then we thought that in order to build speculators, we need to do a proof of concept that it would work. Essentially, that's what this proof of concept was, to show that you could in fact detect an Earth-sized planet from the ground. These are the residuals of the photometry of a brown dwarf that you see has been taken for nearly 2 weeks here. And if that brown dwarf had a 2 Earth radius planet around it, you would see 2 of those white dots reaching the blue line here. The holes are here because it's essentially day, night, etc. And here it's clouds. That happens when you're on the ground. And if you fold everything over one night, this is essentially, again, you would have like a few of those points, like 3 or 4 on the blue line if you had an Earth-sized planet transiting right there. So this essentially showed that in principle, you could detect Earth-sized planets in the habitable zone of their star from the ground. So this was sent. Michael received this funding, then attracted more funding through friends and things like this. And while the call for tenders were sent, analyzed while the telescopes are constructed and then shipped to Chile, we had actually a few problems. The latest telescope was on a boat, and then the boat broke and was just adrift across the Pacific. It's the sort of stuff you never think about. And then ended up in the wrong harbor. So you had to ship the container to another boat, etc., etc. So it takes a while. But meanwhile, TRAPPIST, which had started a pilot program, carried on observing. It had 50 stars. And about 3.5 years ago, quite unexpectedly, we hit gold. And that's where TRAPPIST-1 came. In fact, the first one that we found was TRAPPIST-1c, the second closest planet to the star. So immediately it was noticed. You can see that the event is actually quite obvious in the light curve. This is, again, 1% change in brightness. And then we observed more. Then we found TRAPPIST-1b. Then we confirmed C. Then we confirmed B. Then we weren't sure. Here you see it's 1.5 days, so it means that you have a transit every 3 nights, but then you should have another transit, but it's during the day. So how do you know it's 1.5 days? Well, just call your friends in India and say, up from the Himalayas, boom, from Hawaii, boom, up, so confirmed. And after a few months of observing, we knew that there were at least 2 planets around TRAPPIST-1, and then we had a candidate, planet 1D, where we had 2 transit events quite far apart from each other. And we were there, okay, well, clearly they look like transit, up, they must be the same, so that's the planet, planet D. And we did not know its orbital period, we just knew it was one of 11 solutions, and we left it at that. And then I'm going to show you how we resolved that problem. So the TRAPPIST system, just to give you an idea, this is now a very big team led by Michael Gillon. Now the papers and what I'm going to describe you, so the discoveries were done in 2016 and 17. The latest information about the star is from this paper by Valérie van Routel. Here is a paper by Laetitia Del Rey on the sizes, and Simon Grimm here for the masses of the planet. So all of those are in these papers, all of what I'm going to say. So imagine that you had those 2 events here, and you know that you suspect there's a 3rd planet. You have 11 possibilities, but then some of them are a bit more probable than others, so you trigger the VLT and you think, okay, well, it's fun. On that particular event, there's a good chance we're going to get this putative planet D, and then planet C will also transit. So we'll get 2 planets at once. It's cheaper, so let's go and ask for it. We observe, and lo and behold, that's what we observed. We're like, what the heck is this? And so you have here the brightness of your star, then you have 2 planets coming in, a 3rd coming in, 1st coming out, 2nd coming out, 3rd coming out. 3 planets! We were expecting only 2. All right, there's a 4th planet in the system somewhere. So, okay, but at least one of them must have been, as we thought, planet D. So now we know the period. So let's trigger again a telescope. So we asked our American friends on the Kepler Spacecraft and say, okay, if we trigger on that day, then we will normally see only planet D. We observe. And guess what? Instead of 1 planet, we find 2. Now, so do we have 5 planets, or is it planet 4 that came back? Or, as Michael put it, do we have a double planet? that keeps coming in pair. That would be incredible, wouldn't it? So we thought, okay, well, now we know the period, so we trigger again. How many planets do you think we found on that one? Anyone? 0. So then we knew that we did not understand anything about TRAPPIST-1, essentially. There was something that we totally missed. So then we go back to the Americans and say, well, rather than ask you for 3 hours at a time, please give us 3 weeks. And that's how we solved the problem, essentially. And that's how we have identified the 7 planets. So here is this data set. This was an incredible data set, almost to cry for. Like when it landed, we just never seen something like that. You see here the brightness of the star. You see here time in days. So anything that goes to here is an Earth-sized. Here you have 2 planets at once, so you get to 2% transit depth. And then you observe for 3 weeks. Some of the holes here is because the spacecraft has to turn around to uplink its data back to Earth. But you see transit after transit after transit, all the time, transits. It's crazy. For 6% of the time, you have transits on that star. So this is a really unambiguous detection. And it was like really surprising to us, extremely surprising, that so many planets existed in that system. And so if you collect each of these elements here, you actually reproduce this well-known and recognizable shape. You have essentially this box-like shape of a transit. You see each of those has a slightly different depth here, and that's because the planets have slightly different sizes. You see that each of them is slightly different durations, and it's because the closest planet goes faster than the further out planet, and so they spend the further out planet, when they pass in front of the star, as seen from here, they spend more time in front of it. And that's how you build this picture of a star surrounded by 7 Earth-sized worlds. Now let's look a little at TRAPPIST-1. What does it look like? Well, you see not like much. It's a small star, only a tenth essentially of a sun-like star, very faint, very, very faint. And that's why the planets can be so close to their star and still be temperate. And it's only 12 parsecs away, so meaning something like 40 light years away from the solar system. So it's far and not far in that it's far away in human terms, but close. It's the solar neighborhood. It's within the 500 closest stars to the solar system, more or less. Now the image I want you to conjure when you think of TRAPPIST-1 is the following. So here everything is to scale. So you see that the star is slightly bigger than Jupiter. Here are the satellites of Jupiter. Here are the planets of the TRAPPIST-1 system to scale. And the axis here is not distance, but orbital period. And you see how remarkably similar, essentially, the Jovian Galilean system is to the TRAPPIST-1 system. And in fact, it's even more similar than that, in that Io goes 4 times around Jupiter, while Europa goes twice, and Ganymede goes once. Here we have also an entirely commensurate chain, but we'll go into that in a few minutes. A way to look at it is to put it in graphs. So what we have here is planetary radius in units of the Earth. Earth is here. Here is a distance, a unit of distance in incident flux, so we can compare in a practical way the solar system to the TRAPPIST-1 system. And you see that essentially the dots that we have lie in very good comparison to Earth and Venus. You'll notice also the uncertainties here. All the uncertainties are the same size. And it's not because we know the planet just as well as one another. It's just because now our uncertainties are smaller than the uncertainty on the radius of the star. Remember that the transit method only measures the ratio between the planet size to the stellar size. And so this is our uncertainty on the stellar radius. So that's actually where we can improve the most, is by knowing the star better. Anyone that can measure the star better will tell us more about the planets at this stage. The one thing that happens also is that this is a side view of the planets. You see all the planets actually, compared to the stellar disk, you see that all the planets are actually quite close to one another, and one day we might even see the planets overlap with one another, which is something kind of cool we're expecting. We still haven't captured an event like that. But they're essentially all in a very collimated plane. Another characteristics of the system that we expect, that we haven't measured, is that we expect the planets to be tidally synchronized. That means that essentially you will have a permanent day and a permanent night, the same way that the moon always shows the same face towards the Earth. So I've put that as a question, is tidal synchronization relevant to habitability? It's something that people have been debated about. I actually would not think so too much, but certainly it will have a big effect on climate circulation on the planet. And that's something I think that is interesting for the TRAPPIST-1 planets, is that they're very similar in many ways to the Earth and other planets of the solar system, but also very distinct, and that's one of the distinction, the synchronization. Another element also that people immediately pointed out is whether the planets are stable or not. So you can do that from computation. So now the longest computation have integrated the system for 15 million years and found the system is actually stable. I will also have some arguments from just purely the observations, but it's a hugely important computational problem. In 5 million years, planet H will have done more orbits, twice more orbits than Saturn in the entire Sun's lifetime, right? In 5 million years. So in fact, the fact that it was stable for 50 million years has already shown that the system is more stable than the solar system for 10 times of the Sun's lifetime. It's crazy. That's because things go really fast. We have orbits every few days instead of every few years. Or for Neptune, 160 years. Actually, the first orbit of Neptune since its discovery closed only a few years ago, which is crazy, right? That's one orbit. This already required 10 to the 10 computational steps. So integrating the system for a few billion years, and we think the star is about 7 billion years, is at the moment just impossible. And that's actually a hugely interesting problem. If anyone wants to crack this computational problem, I think there you will have people ready to accept you with open arms. One of the things that is problematic about the stability is that it's hard to also include all of the physics. So tides are important, and we'll go back to that, but the tides of G on F are 3 times the ones of the Moon on Earth, and C on B are 30 times those of the Moon on Earth as they pass by. In fact, they're close enough that the C could cause earthquakes on planet B as it moves by, which is kind of, for the first time, astrology would actually work, right? It's just like, oh, the planet is arriving. So the reason I think the system is stable is that the star is probably 7 billion years and has done many more orbits than any of the bodies of the solar system. So we know that it has to be stable, and there is no real problem there. So now let's look a little at formation, of planet formation. I think it's actually another place where TRAPPIST-1 has made a milestone in addition to the special properties of the planets with respect to habitability. So these are the only papers I found, and there might be more, it's not maybe exhaustive, but I searched for a while of papers talking about planet formation around stars like TRAPPIST-1. And you see that there are 4 papers prior to the discovery and 2 since. So not much has been looked into. And those papers essentially come in 2 flavors. Some of them, tell you that the planets ought to be extremely dry, no water at all, and the other that they should be extremely wet, lots of water. In between, no. And that's interesting. So it means that maybe we can actually find and basically start from observing the TRAPPIST-1 planets, we can start distinguishing between these different flavors. A part where TRAPPIST-1 is particularly important is that it's the first time that we're an order of magnitude away from the Sun. So let me explain. So here you have again this distance, here in incident flux again, so we can compare objects across a wide range. You have stellar mass here. So these are planets with sizes under twice the size of the Earth, and most of them were found by Kepler. And you see they were mostly found around these Sun-like stars. And here we are, an order of magnitude away. That's the first time. You can't find planet an order of magnitude up, because 10 solar mass star basically blow up before you could even form a planet, which is kind of mildly inconvenient, you might say. So the only way that you have to study things is by going down. And I think any good theory, any good physical law should apply over orders of magnitude. So you develop a theory here, and then you apply it 1 order of magnitude down, and you see if it works here. So for the first time, we have achieved that order of magnitude, and I think that's worth celebrating. And why TRAPPIST-1, and hopefully the many planets we'll find with speculoos will teach us about planet formation. Now, there are a few other things related to formation that we can glean from the little bit of observations that we have. So let's look at the occurrence rates that we can deduce around stars less than 15% of a sun mass. So TRAPPIST and speculoos had 50 stars observed, and we detected 1 with planets. We have actually not totally completed the survey of the 50, but we'll assume here that we have. Kepler observed 107 stars, quite badly, but at colors very similar to TRAPPIST-1, and found 2, Kepler 42 and Kepler 445. And this basically implies a rate of 30 to 45%. 40% of stars, about, less than a quarter of the sun, having essentially planets with periods less than 6 days. These are very rough numbers, by the way, just an approximation. If you take Proxima b, which has been found using the radial velocity method, and you calculate the probability of transit the planet has, you find that it has a chance of transit of 1.5%. And it means that if every of the stars like this had a planet rocky in mass within the habitable zone, you would need to observe 66 stars before finding one in transit. And 66 stars is awfully close to 1 in 50 and 2 in 100. So the numbers that are implied here just appear enormous. It seems that those small stars have a lot of planets. Now let's look at a slightly different method and look at the radial velocity method, which has not gone quite to 0.15, but really is about 0.3. There are not many things. Within 5 parsec, you have 37 such stars, and then 9 of those have detected planets, since actually another system has been discovered. And there you get also this sort of occurrence rate of about 30%, which is below a 20-day period. So that's intriguing, because that's a lot of planets on those small stars. And remember, those stars are the most frequent. You have 3 times more stars here than you have here. And then you have 3 times more planets around those stars than you have here. So the best occurrence rate that we have from Kepler indicate that maybe 10% occurrence rate around Sun-like stars for Earth twin is likely, although this is still also with large uncertainties. And so the conclusion that we get from that is that it's possible that there are 10 times more Earth-like planets on these small stars than around there. So the most common rocky world is not around a Sun-like star, it's around a small star. So whether we want to understand planet formation, whether we want to understand climates of rocky planets, or whether we want to understand habitability or the emergence of biology in the cosmos, we can't avoid the small stars, essentially, because they're so numerous. We always have to start by the most numerous population. In fact, they're so numerous that it's interesting. Imagine that we find biology on those, then we've solved our question, is there life elsewhere? Yes, boom. If we don't find it, if we find that none of the planets are habitable, or that they're habitable but not inhabited, they're all sterile for some reason, then we also know, for the first time we will know that at most 1 planet in 10 hosts biology in the cosmos. And we will have done actually a huge amount of work. Already we start placing an upper limit on the amount of biology within our universe. So now let's move a little and try to find planet H. So one of the things that I didn't tell you here is that we had planet H, it's here. You see, it's a small signal here, but there's only 1 transit in 3 weeks. And so we did not have the orbital period of planet H. Now, finding planet H was important because similarly to finding it, we'll actually learn about masses. So one of the things you can notice from this light curve here, this is wobbly, here we have 3 transits in a row. Look at that, that looks similar. Let's go back 1, up, oh, 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 the same sequence. And that's not random. Like if you look at any other data in Kepler, you will not see this. And the reason we see this is because the planets are near what we call commensurate orbits. So B goes 8 times around the star, C goes 5 times, C goes 5 times, D goes 3 times, etc., etc. And the fact that they do that means that the planet exchange orbital energy. And so it means, and you see here transits for D, E, F, and G, And it means that sometimes the planets will essentially kick each other a little bit, gaining or losing eccentricity, and they will have slightly different velocities along their orbit, meaning that sometimes they'll be late and sometimes they'll be early. And if you had a regular orbit, normally all of those transits will line up here to this 0. They would all be on the same line, but you see this one is early and this one is late. In fact, you kind of see that it bends here, in the same way here you have a sort of sinusoid. That's what we call transit timing variations. And those are useful for several reasons, but one of them, it will give us the masses. The second is that this sort of configuration allowed us to find planet H and predict where it was. So 3 body resonances, and that was a question that a member of our team, Brice de Maury, raised. So what you have here is an equation where you have period 1, B, period 2, C, period 3, D. And then if you have a simple integer of a P and a Q, 2 here and Q, 3 here, then you should find 0. And in fact, you find 5 10 to the minus 5 when you do that for the BCD triplet. If you do that for Io, Europa, and Ganymede around Jupiter, you find 0. That's essentially the 3-body resonance, the Laplace resonance. And what's interesting is that you can use this equation on C, D, E, D, E, F, E, F, G, and you always find 0, or close to 0. So the question was, like, if you have F, G, H, you assume it's 0, for which values of P and Q would you get 0, and then I will essentially give you P3, the period of planet H. And you do this exercise, and essentially you find all sorts of orbital periods. And you know this can't be this one, and it can't be this one, otherwise we would have seen the transit again within the light curve. So you can just rule this out, and you can rule this out. Now, which of these is the correct one? Well, I don't know if you remember, but one of the graphs was showing the duration of transit. That is a function of how rapidly the velocity of the planet about the star. And it turns out that all the planets in a planetary system of TRAPPIST-1, this is orbital period, and here's the duration of transit, just follow this nice power law right there. So you extrapolate, you put planet H here, because you know its duration. What do you find? 18 days. 18 days it is. 18.766. So you make a prediction, and then you observe some more. And sure enough, planet D, H, bing, 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 at the 3rd digit, right? Predicted at the 3rd digit. So that's how we basically got the period of planet H. And I think that's quite remarkable, deducing a planet just from a simple relation. Now, this configuration so seems to be a feature of TRAPPIST-1. It is also the way that we detect the masses, right? We can't essentially do radial velocities on this star, unfortunately. If you were to use the equation I showed you early for the radial velocity motion, you would find that typically a planet like the TRAPPIST-1e in the middle of the habitable zone would produce an oscillation of about 2 meters per second, which sounds large. However, the star is actually quite faint. And so if you had 2 stars, a G-dwarf, like a Sun-like star with a habitable planet around it at 9 centimeter per second motion, and a TRAPPIST-1-like star, same distance, right, with a 2 meter per second motion, the fact that TRAPPIST-1 is so faint means it's actually 5 times harder to find that planet using the radial velocity method than around your Sun-like star. So we needed another way to do that. And thankfully, nature was cooperative because of this transit timing variation and the fact that all planets are in commensurate orbits. So you see here this TTV signal, so it's basically the lateness and earliness of the transit as a function of time, and you can see that they oscillate, and sometimes quite a lot. You see here, you're getting basically a change of almost 2 hours. 2 hours, right? So these are short orbits, so it would be like skimming a week of a year every now and then, which would be good some years and bad some other years. But essentially this motion here is a complex function of the ratios of the planets to one another, eccentricities of the orbits, and the ratio of the mass of the planets to the mass of the star. Again, we don't measure directly the mass of the planets, we only measure the ratio of the mass of the planet to the ratio of the star. The one thing that we measure in absolute term here, combining transit timing variation and the transits themselves, is the density of the planet. So that we measure in absolute terms. So what do we see? The masses, here they are. You see planetary mass in units of the Earth, same thing, incident flux. You see Earth here, Venus here, and you see how the planets, basically again, nest very well within the solar system. The other objects that you see here are the detected planets. In the transit and radial velocity method, you don't quite see them. There are a couple just there as well. What we detect in absolute terms is the density. And again, the planets here are basically between 4 and 6 grams per centimeter cube. Again, I have Venus and Earth here, and you see how close we are. D, look at that. Exactly on the moon. Venus, totally compatible with planet C. Really remarkable. Now think of those planets, the most interesting is TRAPPIST-1e right there, which is slightly overdense compared to the Earth and slightly further away from the star. You see it receives about half the flux from the star as Earth does, which is actually quite good for a tidally synchronized planet about an M dwarf. So planet E is the real prize here in terms of search for life or assessment of habitability. In a mass radius diagram, Earth at 1,1, Venus slightly shorter. Here, this line, Mars is here. You have the 3/4 silicate, 1/4 iron. And you see that it reproduces the solar system remarkably well. You see where the TRAPPIST-1 planets are. There are 2 here, 1, and then another group there. You see they're slightly underdense here, slightly overdense there. So this is actually astonishing that actually the worst offender here, the least dense planet is planet B, which is the closest to the star. And so far, those measurements might change a bit as we refine our transit timing measurements, but essentially they imply either a very thick atmosphere for planet B or an important layer of water. In any case, some sort of volatile. What's interesting is the diversity, though. You have underdense planet and an overdense planet in the same system. So the formation theories that we have, which was either the planets are dry or they're wet, here it seems that we have both if water gets involved. This is preliminary. We will have more data in the coming year on this. Now let me show you TRAPPIST-1 in context of other planetary systems. So this is the same graph I showed you earlier, except that instead of mass here, we have mass ratio. So it's the ratio of the mass of the planet to the mass of their host. And you see that the graph has essentially not changed. And that's because most of the detection we had were on Sun-like star. Now it turns out that TRAPPIST-1 falls here. It falls within the super-Earth population. It overlaps with it. That's sort of interesting because this population is the dominant population around Sun-like stars. So could it be that TRAPPIST-1 is the equivalent of a super-Earth system but around a low-mass star? So in order to plot TRAPPIST-1 on this, we had to move by 1 order of magnitude down, right? From Sun-like star to 0.1 of a Sun-like star. Now let's move an order of magnitude down, and then we have a 10 Jupiter mass planet with satellites. Do we know that? No. So we can't add this. But if we move 1 order of magnitude further down, we have Jupiter and its satellites. So let's plot this. Oh, look at this. And it turns out that if you plot any of the gas giants and their satellites, they're all here as well. So I don't know what that means. I don't know whether it's a coincidence or not. We need more systems like TRAPPIST-1 and plot them here, find out. But it turns out that the mass ratio between if you take each of the planets in the solar system and add all the satellites, divide by the mass of the planets, you always find a universal 10 to the minus 4, and we have essentially the same for super-Earth around G-dwarfs and TRAPPIST-1 around 10% of the sun mass. So it's sort of odd because we still don't understand how super-Earth and sub-Neptunes form. And we always thought we didn't have one in the solar system. So this is the most common mode of formation. Now, wouldn't it be funny that the place that this formation mechanism happened is not on the planets of the solar system, but around the gas giants? And that's a question I'm leaving out there because we don't have an answer for that yet. But that would be particularly interesting, I think, to have an answer, either a yes or a no. So let me start ramping it down. I'm going to briefly go through some of the reasons TRAPPIST-1 is interesting. Then I'm going to go through a couple of interesting things to consider about TRAPPIST-1 and then describe briefly the atmospheric work. So TRAPPIST-1 is optimal for atmospheric characterization. I will go into that. Comparison is next slide as well. So the good chance that we have is that we can compare between 7 worlds. We have the chance to study habitability in non-strictly Earth-like condition, but containing many of the same characteristics as Earth or Venus have in the solar system, we may be studying the most common type of planet. And I think that's the main advantage that we have. So the question of how frequently there is life in the cosmos can be, I think, more readily addressed by a system like TRAPPIST-1. And currently, we already have the best measured in terms of mass precision, best measured planets out there, outside the solar system. So let's look at the power of comparison, I think. For much of the work in terms of identifying biomarkers, we always thought of a planet in isolation. The chance that we have here for TRAPPIST-1 is that all the planets came from the same nebula. They have a similar flare history, meaning except for the distance. So this one will have received more insolation from the star than this one, for instance, but you can account for that. And they have a similar impact history, we think. So it means that if all of the planets have a CO2 atmosphere, except planet 1e, which has a nitrogen-oxygen atmosphere, then I think it would be very hard to not accept the argument that something funky is happening at the surface, essentially. And that's the chance that we have. And whatever it is, actually, it could be a half CO2, half methane atmosphere, anything out of equilibrium on a planet that just happens to be quite hospitable for liquid water would actually be remarkable. So having 7 planets is a huge advantage. And if we find more of these systems, I think we can play that card. So that's one of the first points that I wanted to bring. Another point that TRAPPIST-1 is interesting for is to do some geology beyond the solar system. So the tidal heating that we expect is actually quite large. You see here the eccentricities as a function of time. This is work done by Emeline Beaumont. I forgot to actually put her name on this, sorry. These are the eccentricity as a function of time of the planets as they interact with one another. And you see here planet B, eccentricity is tiny, but it's enough to essentially make it have a tidal heating like Io has around Jupiter, which is essentially about 10, so 3 times higher than Io. Earth, by comparison, is quite small. So the planets are under quite a different regime than ours. But in fact, this might be handy, maybe not handy in a search for life for planet B and C, but certainly to learn about something else. Trying to identify gases as traces of planetary interiors, again for the first time. Again, the planets transit regularly, so it's easy to do. I'm going to show you we could maybe, using this mapping method, try to geolocate a volcano, the same way that we do essentially in thermal imaging on Io. And doing that, because our planets are quite big, maybe see the contours of plates if we find volcanoes. Tides also, and that's a paper we just got accepted in Icarus, are sufficient to cause crust fracture on close-in eccentric planet and drive tectonics. So those planets may have actually plate tectonics driven by the fact that their orbit is slightly eccentric. And that's good, because it means that if we know that the chance of tectonics on these planets is higher than any other, then we can look for these gases, try to find whether those gases really happen every time that we have this, and then we go for planets that are not tidally disrupted, so to speak, and try to identify similar gases elsewhere and find out whether plate tectonics is a function of planet mass or planet radius or whatever else you want. And we talked about the earthquakes. So the way, actually, I'm going to show that result here. So that's essentially the frictional force that you need at the moment on Earth to fracture a plate and drive it using convection. And that's the force that the mantle imparts. You see, like it's way off. And that has been a problem from the beginning. It's a huge problem in geology. How do you initiate plate tectonics on Earth? And one of the ways geologists and geophysicists have done is to weaken the plate. And if you put water, you weaken it. And this is parameter here is the weakening parameter. And you get here. If you have an ocean, you can weaken this frictional force here to here. But you see that it's off from what the mantle can give you. The tides here are essentially these here. This is an angle dependence on the planet, so the tides are angle dependent, azimuthally dependent, but you can see that we're orders of magnitude above essentially the weakened plate of Earth, and certainly above what the mantle can give you. So that's one way that I think exoplanets are interesting to teach us about processes that we study on Earth. Now let's go to the atmospheres, because that's, after all, what we're here for, right? We want to identify biomarkers eventually, or at least study climates of these worlds. So here are the data that we did. So we did some reconnaissance of the planets using the HST. Here you have different wavelength channel. You have planet C and planet B transiting one after the other. The reason we do that is because it's, again, you get 2 for 1. It's cheaper and easier to access the HST to do this. And so you measure the depth here, how deep this signal is as a function of wavelength. And essentially, you create this graph. So here is the size of the planet as a function of wavelength. Here are the data points in white. And you see that, by and large, within uncertainties, they're flat. These are models of what we would have expected if the planets had a hydrogen helium envelope. So remember that at the beginning, when we looked at TRAPPIST-1, we did not know whether they were small versions of Neptune or really rocky worlds. So if they had a hydrogen helium envelope, we would have seen this warping signal, which has been ruled out at 19 sigma. And so essentially, we now know that the planets either have no atmospheres or they have an atmosphere with a higher molecular weight. From the density measurements that we have using transit timing variation, it looks likely that they have at least a layer of volatiles. So the atmosphere looks good, although we cannot quite reach it. I will point out also the uncertainties here as 300 parts per million, right? This is here the unit, 300 parts per million. That'll come back in handy later. So the size of this structure here depends essentially on the molecular weight of the atmosphere. So essentially, if you don't detect, you can see that you can place a sort of upper limit on the molecular weight by the lack of a detection. And so I don't have planet B and C like here, but I have the other 4 planets here. And you can put 2 sigma upper limits on the molecular weight of the atmospheres. And you can see that, at least for the outer planets, we already rule out a sort of composition like the gas giants. And essentially, as we get more and more measurements, we're going to get closer and closer to Venus and the rest. These are models by Caroline Morley. So you see here, again, this transit depth as a function of wavelength. And you see that the unit here is 100 parts per million. 100 parts per million. And here you compare various atmospheres for TRAPPIST-1c between Venus, Titan, and Earth in terms of composition. Now, this 100 parts per million is important because our current uncertainty is 3 times larger. So it doesn't look good, right? But it was done only in 1 transit with HST. The fact that this is 100 means that if you had 10 transits with HST, your uncertainty per wavelength beam would be 100 parts per million. And already you start reaching the right regime. Now, thanks to James Webb, we will be able, essentially, within 10 years, essentially, we will have data able to distinguish whether TRAPPIST-1c is Venus-like, whether it's Titan-like, whether it's Earth-like, or whether it's something else. We might not be able to say that there is life there, we might not be able to give the exact abundance of whatever molecule, but we will already be able to tell you whether it is more Earth-like or more Venus-like. And the numbers that Caroline basically put out, you can see here, these are the number of transits that you need to study these systems. They're quite small. They're in a handful. And that's where TRAPPIST-1 holds a huge promise. TRAPPIST observed 50 systems. Speculoos will observe 500. We started. We hope to detect dozens of these worlds. We know of only 2 Earth-like planets so far, Venus and Earth. Right? Now compare them. How different are they? Right? Now imagine you have 30 of them. What will we find? Will it be 30 Venuses, 30 Earths, or 30 completely different kind of planets? We have absolutely no idea. And so everything is wide open at this stage. But that's what I think surveying small stars is so important. Whether or not you're interested in habitability, I think studying the climate of these worlds will basically open the door to studying the climates of rocky worlds throughout the cosmos. In my final slides, I will say a word of caution. Astronomy is coarse. We won't measure something very precisely like you can do in a lab or you can do collecting rocks on the surface of the Earth. We won't be able to measure something precisely. However, we have a large sample. With a large sample comes other opportunities. You can measure, depending on your star, by using younger stars. You can find younger planets by using planets that basically orbit brown dwarfs, white dwarfs, or red giant that evolve and change how bright they are. Planets that used to be habitable or no longer habitable. Planets that used not to be habitable now have become habitable. You can actually start measuring the timescale of life's emergence eventually. So you won't measure it precisely, but you will have an idea in something that you can't do without a large sample. Answer this question: are Archean conditions necessary or sufficient? Was it just luck that life started early, or was it absolutely necessary because there is only a small window during which life can start, otherwise it won't? We can also check whether any of the biomarkers coincide with what we define as habitable zone or habitability, generally speaking, and try to test those ideas. The questions that we can ask are: how frequently does biology emerge? And because we have a large sample of planets, notably a large sample of small stars, we can start answering that, or place an upper limit if we don't detect anything. Because I think it's interesting to know that it's one planet in 100 or one planet in 1,000 that has biology. In which conditions do we see tectonics? I think that's important. What is the optimal UV environment? UV is both destructive and also a chance. It gives interesting chemical reactions. We can also ask for Earth twins or moons or Jupiters, like people have argued, relevant at all to habitability, the emergence, and how life thrives on the planet. Is tidal locking achieved? Because we don't know. Venus ought to be tidally locked, so does Mercury, and yet none of the two are. And finally, did life originate at the surface or deep in water? By looking at enough of these objects, you will be able to do that. And so finally, I'm going to say that the study of alien environment has started. Stay tuned, and within a decade we will have a lot more to talk about. Thank you very much.